Hi everyone, I'm Lucy. I'm a PhD student at Monash University in Melbourne. Thanks for coming to my talk on gravitational waves from tidally interacting white dwarf binaries. So, since the first coincident detection of a neutron star merger in electromagnetic and gravitational radiation, astronomers can't seem to get enough of talking about multi-messenger astronomy. And doing this with binaries that aren't even merging should even be a part of this. And one important thing that I've learned during my PhD is that if you take some of the letters in that phrase and rearrange them, you can actually spell astroseismology. So it's actually not a coincidence, and I'm going to spend this talk showing you how we can do astroseismology with gravitational waves with LISA. So traditionally, you can measure the normal oscillation modes of stars, which depend on their structure, in electromagnetic by measuring the timescales over which the star's luminosity varies. So if you know the star's mass and radius, you should have a pretty good idea of the mean density, which means that you know roughly what the fundamental mode is going to be. So if you observe a frequency that is higher than that, it'll be a pressure mode, and frequencies lower than that will be gravity modes. So in this talk, I'm going to tell you how we model these white dwarf binaries that will tidally interact in the LISA band using a normal mode analysis. I'm then going to present an expression for the non-zero eccentricity induced in these systems, and you'll see that it depends directly on the stellar structure. And then I'll go through how we can do this with an example. So just for reference, I'll show you the LISA and another planned space-based gravitational wave detector DECIGO sensitivity curves. So the most numerous source in these frequency bands at their most sensitive is going to be white dwarf binaries. So there's millions of white dwarf binaries in the Milky Way, and LISA should be able to detect tens of thousands of them. So what does a gravitational wave signal from a single white dwarf look like? So here I've just made an example system. So typical 0.6 solar mass carbon oxygen binary. I've given it a 5-minute orbital period. Which is an orbital frequency of 3 millihertz, and we integrate it over 5 years. So for this system, the merger timescale from gravitational radiation is on the order of megayears, which means that even over the 5-year period, LISA would not be able to distinguish any kind of frequency change or chirp from gravitational radiation. So that means that when we see this, it'll just be a delta function at 2 times the orbital frequency. So because this signal has no finite width, because we can't resolve its width, the signal to noise will be on the order of 100, and we can actually just count that from looking at the factor that this star is above the noise. So back to the sensitivity curves. So it's the strain from many white dwarfs in the Milky Way that go on to make this integrated white dwarf foreground. So I've just put an example from Ashley Reuter in 2010. But also I've included the 2 fastest detached white dwarf binaries that have been detected in the optical. So these also have signal to noise ratios on the order of 100. And I just want to point out that these are the kind of sources that I'm going to be talking about, rather than the ones that we can't individually resolve. Okay, so for the most part, it should be fine to model white dwarf binaries as point masses, like they're far enough apart to not tidally interact, and they're also expected to be in circular orbits from a history of either common envelope phases or tidal interactions. But the thing is that many of these more rare and louder resolved binaries are going to be so close that tidal interactions are important. So this is just a still here of a binary on the kind of length scales we're talking about. We're talking about stars that are only a few stellar radii apart. So we model them like this. So you just have a Kepler orbit, and then you have the normal oscillation modes of a polytrope. So that's a harmonic oscillator. And then they're coupled with an interaction term through which they exchange energy and angular momentum through. So just note that we've coupled the orbit to the fundamental oscillation modes of the polytropes. We also include post-Newtonian corrections to account for geometry effects in GR, and we also include the effect on the orbit of gravitational wave emission, so the radiation reaction. So what I want to focus on here is this tidal coupling term. So this is actually going to determine the strength of the interaction between the orbit and the tides. So just note that I won't show it, but this term depends on things like stellar structure constant. So in particular, you can write it in terms of the apsidal motion constant, or you might have heard of the Love number, which is related to that. So that's a measure of how deformable the stellar material is. The coupling strength also is going to depend on how close the stellar surfaces are. So another way of thinking of that is just the ratio of the star's radius to its separation. So I said before, we're dealing with binaries that are only a few stellar radii apart. And it'll also depend on the mass ratio. So one of the main results in this paper is an expression for the eccentricity evolution of these binaries. So what you see is, instead of it just being 0 for all time, over one orbital period you get some peak of some amplitude A, let's call it A. So the amplitude depends directly on that stellar structure constant, the apsidal motion constant, and also that separation, how close the stellar surfaces are. So via this expression, we can see that the more deformable your star is, the more willing it is to sort of change in the presence of a tidal potential, and also how the closer the stellar surfaces are, the larger that induced instantaneous eccentricity will be. So yeah. So let's go through how this works with an example. So let's use a high mass binary made from 1+1 solar mass carbon-oxygen white dwarfs. So assuming a polytropic model and setting an orbital period of half a minute, this binary will be separated by 3.2 stellar radii. So this binary will merge in the order of 100 years. So unlike that example I showed earlier of point mass white dwarf binary, LISA will actually be able to resolve a frequency change or a chirp over the observing time. So yeah, we'll put it at 1 kiloparsec away, so a bit optimistic. And just remember that the amplitude of that instantaneous eccentricity is given by the apsidal motion constant and how close the star's surfaces are. So if we use that prescription and put in all our stellar structure constants and orbital parameters, we would predict an amplitude of that instantaneous eccentricity on the order of 0.01. So that's in grey here in the top plot. And then on top we've put the the actual numerical simulation of this binary. So indeed, that maximum over the orbital period is happening around 0.01. So I guess the question now is, what does this do to a gravitational wave signal? Because this is clearly a deviation from a circular point mass binary. Because here I've put the separation in time. So the relative separation of these things is actually changing on the orbital timescale because of this tidal interaction. Okay, so this is the signal. So just let me explain it. So the thick red is the strain in the 2F harmonic. So that's similar to what we saw earlier, except like I said, because this thing is merging relatively soon, in 100 years, the signal actually has a finite width. So what I've drawn in the thin lines here is the equivalent not finite width signal that has the same signal to noise as this finite width signal. So that's just for you to basically look at and count the factor above the noise it is to say, okay, I think the signal to noise, so the signal to noise for this, for example, the 2F harmonic is around 8,000. So the thing that we see that's different when we include the tidal interactions is this power at the first and third orbital harmonics on the left and right in blue here. And this was not present in the circular approximation. So another result in the paper is that we actually have an expression for the waveform in terms of each orbital harmonic. So if you know what the amplitude of that instantaneous eccentricity gets to, then you know the ratio of how high the blue sidebands are compared to the red. So you could calculate that roughly from that waveform, but I'll just tell you what they are. So the signal noise ratios for a match filter template for that first and third orbital harmonic in blue is on the order of 10, so 30 and 50. So I guess the point of this is not to improve your signal to noise of these super loud signals by including these sidebands. The point is more you'd want to individually measure these sidebands as part of the same binary, and then measure the ratio of them, and then ask, well, what does that tell me about stellar structure and some of the orbital parameters? Okay, so just to summarize that, I guess for these binaries that are sufficiently close, they'll be loud and they're resolvable. They're not going to be circular due to this presence of the tidal potential. These instantaneous eccentricities can reach on the order of 0.01, and this is detectable in gravitational waves with LISA. And so a measure of that ratio will tell you about the stellar structure, but I think ultimately it'll help constrain the masses, the individual masses, the separation, and also the spin in the binary. And this is totally different to anything we've ever seen in electromagnetic. So yeah, that's it. Thank you.